right? These values are still very, very big, right? So although from the source, you know this CD is very small, but for a attacker point of view, you don't necessarily know this CD, this interval. You only need know this BD. Okay, so here we did some comparison with the constant rate scheme. So in this figure, the x-axis is the mean of this real event interval. So which means the real event generated, the mean is every 20 seconds there's one real event, and the average delay you can see from this for constant rate scheme. So here you can see this is so we assume here this dynamic traffic, this packet rate is in one. So here is let me see. The interval, average interval is 20 seconds. So in this case, for this constant rate scheme, so it's about the half of that, right? So 10 seconds. But in our case, because we give this adjust this distribution, this interval for the real event. So you can see this. So here, the delay for this real event now is becoming very small, less than 1 second. Okay, so this is a very small figure. So basically here, you may ask, okay, because this is just one event, right? One real message. If you have multiple messages, you need to transmit. For example, if you're not just report this, this like a panda is here, you will report some additional information, like what is the panda is doing. So you may not be able to use one packet to hold all this information. You have multiple of them to send. So in this figure, you can see that we do different comparisons. So the traffic pattern is for real event. This is one, another one. So the interval is big, but in this second traffic pattern, the real event pattern, so you have 3 packets sent in a row, and in this case you have 5 of them sent in a row. So you have more packets to send. So in this figure, we show that there's another scheme called probable rate, which means you just use the exponential distribution, exactly follow this exponential distribution to determine next time interval. So you can see that this is the So this is the schedule the next time when you can send you should send this you can send this next message. So in this case, let me see, this is the real event, and this is the actual time when you send the next one. So you can see that in this case, the first real message is sent in this time, second one will be here, third is here, right? So actually the third one, this event occurred at this time, but now it's delayed to this point, right? So if you have the first one is occurred at this time, but the second time is here, right? So the delay is is big, according to just follow this exponential distribution. But in our case, because we use this, because we adjust this interval for real events, right? So we can see that this delay is very, very small. For the so this is a real the actual time, and this is the real event time. This is actual time. So in this case, the delay is not that big. But of course, here if you have more packets to send, real message to send, in sequence, then the delay will be larger and become larger and larger. But still, it's much better than this, this other scheme. And if you have more to send, like 5 packets to send, then it will become even larger. Because that's the part of the recovery. Because you cannot always give the preference to this real event, right? Because otherwise, you have many packets to send, it will be skewed. You have to recover them by adding increase this interval. So we are always, proactively doing this testing and increase the interval, so then make sure this mean is still within the range. So this is the figure show this average delay. So compare these 2 schemes, and our scheme is much better. And with of course the advantage of doing this will be will be less if you have more real message to send in sequence. And the security property, which is the alpha epsilon unobservability. This is based on definition is clear because we do this AD, the Enderlin-Darling test. So Enderlin-Darling test actually based on the same idea to measure this distribution like the CDF. So because we already did this test when we send the next one, so it will automatically meet the requirement for the first requirement in this our definition of this unobservability, alpha epsilon unobservability, and because the mean is also always checked and also recovered, so it's also within that range controlled by epsilon. And then, so we think about this issue. We assume attacker will do the statistical test, but we cannot limit it. Attacker must use Darling test as we used. Attacker can use some other tools, right? So maybe you can do a KS test, right? That's also very well-known testing method. So in this way, so we assume attacker can do different. So here's the Darling test and also KS test. So there's a trade-off. We notice, this for attacker point of view, the false positive and false negative. You always there's the trade-off. For example, in this time point, this is when you do testing, right? You have the significance level. You can control. So in this case, so this is the false positive for this two curves. These are the false negative. So you can see that if you want to have 0 false positive, then the false negative will be almost like 1. In this case, the KS test. And then now if you can accept false positive more, then the false negative will also decrease. So that's the best attacker can do. You cannot decrease both of them. And we also did this mean test. So mean test here, the goal attacker is trying to see if the mean has been changed. But we use something called a sequential probability ratio test. So in this test, it's kind of hypothesis test, but the difference is now you have you have 3 conditions. So it's like let me use this example instead. So you have in this case you have 2 alternatives. The first alternative is H0, which means now this the observed mean is larger than the population, or larger or equal to population mean. So in that case, you will not suspect that if there's a real event embedded there, because your goal is to reduce the time for the real events, right? So that there will if this observed the mean is larger than that, of course there's no event embedded, real event embedded. So you don't suspect that case. You only suspect that case when this observed interval is below the certain interval of this population mean. So this is attacker's parameter, the epsilon prime. Attacker can choose, because we cannot say okay we use this the like alpha 0.05. Attacker must use that. Attacker can use different parameters. So basically in this case, well, either it's larger than this or it's below this. So there's a range, right, which is uncertain for attacker. Right? Either it's between this value and this value and this mu. So in this case, attacker will continue the test. So you will receive more samples, the data, right? So you observe this network, and once you have more data, you want to use that information to see if you can draw a conclusion. If not, then you keep collecting data. So this is the way the SPRT works. So it fits our scenario very well. So we assume that once we use this test, then so here's some of the results. We show that attacker can use its own, like let me see, the alpha prime and beta prime is the false positive and the false negative acceptable to attacker, and then the number of observations attacker will make, and this is the range you will consider. This is this determine the lower bound. So the result here shows that okay, after the attacker has collected 2198 this events, the intervals. Now the attacker will make a decision, because either you accept it or you accept the H0 or H1, right? Otherwise you keep collecting more data. So the result here is in our test the attacker accepts the H0, which means the attacker say okay, there's no event. Actually in this test we embed half of this real events into this sequence. Half in the time interval we have this half of them are real, but the attacker can after collected so many samples, decided to accept it.